Excellent. So a couple things up here. Homework 5 is due a week from today, so you got a lot of time to do it. Just keep in mind next week is fall break, so we don't have class Monday or Tuesday. I'm not going to post any video or anything like that Monday, so keep that in mind. You have a week to do it, but we won't meet again until next Wednesday. You can send me emails. I'm not sure if I'll be available Monday or Tuesday, but you can try anyway. If not, I'll get back to you first thing Wednesday. The lab this week is for Group B only. So Group A did the experiment last week. It's collision. This week is Group B. And we'll meet in room 212 as usual. And I gave you the test back. The average was 80%. So what I want to go over is a few selected problems. And then if you have questions on other ones, we can take a look at those as well. Okay? So make sure I added the test up correctly, by the way. Average was 80%. So the one I wanted to mention was, well, a couple of them. Number 4. So that's the one where a boy kicks a football, initial speed of 20. Oh, you can see it. Initial speed of 20. Okay, angle of 30 degrees above the horizontal, so that's theta. What is the horizontal distance to the point where the football hits the ground? Now the practice test one was just, I think, what was the horizontal velocity at the highest point, something like that. This one's not asking the same exact question. A lot of people answered the practice test question, what was the horizontal velocity at the highest point? This is actually asking for what is the range. So several different ways of doing this. Probably the easiest way, most straightforward way maybe, is just to use the range equation. And the range equation, that initial velocity is the overall velocity, right? This velocity is made up of an x part and a y part. In the range equation, that's what that velocity is. You don't have to figure out the x or y part, you just use that. And then it's the sine of 2 theta. A few people add sine of theta squared. So make sure that the formula is working out, that you have it written down correctly. And then g is just 9.8. So when you do that, you get, put in all the numbers, you get, I think, 35 meters. Which turns out to be close to, some people got a close to 35 answer by doing finding out the x velocity and then multiplying it by 2. If you do that, you get a number close to 35, but that would be twice the x velocity. The units aren't correct or anything like that. So although you might have circled the correct answer, you have to show the work to justify the answer. Okay, so you've got to show how you can get 35 meters. Okay, any questions on that one? Okay, and then another one I wanted to mention was number 7. Human reaction time is usually greater than 0.1 seconds. If your friend holds a ruler between their fingers and releases it without warning, how far can you expect the ruler to fall before you catch it? So pretend Rick is holding a ruler and he lets go of it, and then my job is to, as quickly as possible, stop it. So the ruler starts from rest, falls a certain distance, and you can judge by your reaction time by closing your fingers. When he drops it, there's going to be some amount of time. We could use 0.1 seconds for this problem to figure out how far it actually falls. Okay? So we've got all the kinematics equations. This is really a free fall question. This is the one that comes to mind for me. We could use this to figure out how far it's actually going to fall from rest, right? Delta y, that's displacement. We'll just take the magnitude of that. Initial velocity, it's just starting from rest here. And then 1/2 at squared. we could figure out how far this thing actually falls in a tenth of a second. And then don't forget, this is negative 9.8. That's the free fall acceleration due to gravity. So when you put those numbers in to this equation, this is the part that's left, you get something like 0.049 meters, which is 4.9 centimeters. It's kind of fun to do this, actually. You could do it with somebody that has holding a ruler. You think you could get it smaller than that. You can practice it, but there still is some reaction time. The information has to go from your brain, from your eyes to your brain to your hand, so there's some amount of time. So you could do this from reverse, measure how far it falls, and then work backwards and figure out how long it takes. Okay? So that was probably the most difficult one, I think, on the test. Okay. And then also number 8. Number 8 is the dog jumping off the pier problem, basically. So a girl throws a rock horizontally. Okay, so there's no y velocity initially, at 10 meters per second. This way. I drew it here, but really it's going to go like this. It's the same exact problem as the dog jumping off a pier, really. It falls 20 meters to the water below. So in terms of displacement, this would be minus 20 meters. How far does the rock travel horizontally? So what is delta x? Okay, so it's a projectile motion problem. This is in 2 dimensions. The only thing that we have in the x direction is this. So if I solve for delta x, this would be the x velocity times the time. So we know the x velocity, that's given in the problem. That's the 10 meters per second. So don't mix that up with the y velocity. This is thrown horizontally, so that's x velocity. The initial velocity in the y is actually 0 because it's thrown horizontally. Okay, so if we knew the time, because we know the x velocity, we could figure out the displacement. Luckily, we can get the time from the y direction. We know the y displacement, initial velocity in the y. Don't forget, you always know the y acceleration, negative 9.8. So we can put that all together to figure out the time. So we've got a couple of kinematics equations that have time. One of them has final velocity and initial velocity. We don't know the y velocity right before it hits the ground. You can't say it's 0 because it hit the ground. You have to know it right before it hits the ground, which we do not know. So this one actually doesn't really work for us, right? If you're trying to figure out the time, okay, you know this and you know this, but you don't know the velocity right before it hits the ground. So you can't really use that one. You can use this, though. That's the other kinematics equation that involves time. Okay, so initial velocity in the y is 0. So this term is 0. Multiply both sides by 2. Divide by acceleration in the y. Take the square root to get t. So if you put all this information in, the time turns out to be about 2 seconds or something like that. And then 2 seconds times 10 meters per second, you get 20 meters. That's how far over you go. Okay? All right. Very good. Any questions about that one? That was probably the next hardest one. If you remember at the review, I said make sure you look back at the dog jumping off a pier problem. So it's really the same problem. This is just a ball being thrown. Okay, any questions on that one? All right, what about any other ones? The other maybe honorable mention one I can talk about is number 10. An object of mass 10 kilograms is pulled on a horizontal surface by a force of 50 newtons to the right. I'll just call it like applied force. 50 newtons to the right. The object is accelerating at 1 meter per second squared. What is the frictional force? Here's the free body diagram. We've got this applied force, 50 newtons. We've got friction this way, normal, the weight. We want to know how much friction is. Well, we can figure out the net force. I think the practice test had something like how much was the net force or something like that. The net force is m times a. We can get the net force, right? Here's m times a. The net force is 10 newtons. So if the net amount is 10, friction must be 40 back the other way, right? And then the net force turns out to be 10, right? 10 times 1. Don't forget, that's where I got it from, m times a. So the frictional force is 40, okay? That was a common thing people found out, the net force, not the frictional force. Okay, that's the other one that maybe I should have mentioned. So do you have any questions on any of them? If not, think about it. That's the first test. There's 3 of these tests, 3 of these midterm tests, and then the final. Each of these is 10%. So if you didn't do as well as you wanted to, take it seriously, but it's not going to ruin your overall grade, really. It's 10% of the overall grade. If you did really well, keep doing what you're doing. It's working for you. If you didn't do as well as you wanted to, change something up, send me emails. We can meet before or after class, whatever you want to do. Yeah. Oh, yeah, maybe that would be better if it's a specific one, yeah. Okay, yeah, good. Yeah, they're not set in stone, so maybe I missed something, let me know, we can talk about it. Okay. Any other things to mention? Okay. So I gave you a video on Monday, basically finishing up most of Chapter 9, not all of Chapter 9. So I thought what we could do today is start with some problems, finish Chapter 9, and then how much time is left, we'll see. Then we'll get into Chapter 10. Okay? Good. So this week, just to repeat, we're here today. Group B is on Thursday. Next week, we don't meet Monday. It's fall break. We will meet Wednesday. And then Thursday, we won't actually meet. We will actually do an online lab. And I'll make a video of me going through it, that sort of thing. So just next week, the only time we actually come here is on Monday. Or, no, on Wednesday. Wednesday. Okay. Very good. So I thought we could just start with some problems. Before that, let me give you a little refresher on what we've been doing. We've got this impulse relationship. This is the one genre of problems. We've done a few of those already. And then the other kind are collisions. Oh, forgot a big part of this one. F times delta t. These problems are good for force, time, mass, and velocity. Now, if the outside force is 0, which is the case with collisions, the initial momentum is equal to the final momentum. Okay, just put a little vector sign to remind you, look at the x direction separate from the y direction. Okay, so that's really what this whole entire chapter is about. The lab that we did, Group A last week, Group B this week, goes with collisions. Or explosions, same idea. Okay, so with that in mind, I thought we could start with some problems. And this is one of them from homework 5. So if you log into Brightspace, look at Mastering Physics, you see homework 5 is due next Wednesday. Homework 6 is due the Wednesday after that. Homework 7 is due the very week after that. So they're all there for you. I don't like to do them too early. I don't want to put a lot of pressure on you. You have a lot of time to do these things. So they're all there for you. This is on chapter 9. Homework 6 is on chapter 10. And then homework 7 is really over mostly chapter 6. We're going to go back to that. Okay. It's there. Just I got it up early. You don't have to start working on it immediately. We haven't even talked about it yet. Definitely work on homework 5, though. Okay, in this one, a student throws 140 gram. Okay, so be careful. That's not kilograms, that's grams. We'll have to convert it to kilograms. With a speed of 8.5 at the side of a schoolhouse where it hits and sticks. What is the magnitude of the average force on the wall if the duration of the collision is 0.17 seconds? Okay, so let's write down everything that we know for this one. Okay, so the mass is 140 grams divided by 1,000, 0.14 kilograms. Initial speed of 8.5 meters per second. It sticks to the schoolhouse. Okay, so it must go from 8.5 down to 0. This takes 0.17 seconds. And then we want to know the average force. A couple ways of doing it. If you really wanted to, you could figure out the acceleration. Because you know the initial velocity, final velocity time. You could figure out the acceleration, and then when you have the acceleration, you could figure out the force from Newton's second law, the net force. That's the only force that's actually slowing this thing down. Or, knowing mass, velocity, time, and we're looking for force, we could use this impulse relationship. So force times time, mv final minus mv initial. Now the final speed is actually 0 because it stops. So force times time minus mv initial. So the force, I'm just dividing both sides by time. Now this is going to come out to be negative. That just means it was moving one way, the force is the other way. When you do the Mastering Physics, it just wants the magnitude of the force. So you don't have to enter the negative sign. That's the meaning of the negative sign, though. It's just the opposite of the way it was moving. Okay, so we've got 0.14 kilograms, and then 8.5, and then the small amount of time, 0.17 seconds. So whatever that comes out to be. Something a little bit less than 8.5, I can tell you that. But I located my calculator, but I forgot to bring it. Anybody have the number? .2. Anybody else get that? So check it out if you didn't. Oops. Newtons. Thanks, Rick. Kilogram meter per second is a Newton. Okay? It's 14/17 of 8.5, so that seems like it could be right.
It's actually 7.
7.2?
Yeah. Just 7.
Just 7, okay. Okay, good. And then just enter, 7, not the negative sign, because we just want the magnitude. All right, good. Any questions on this one? You might have different numbers, so be careful. Okay, so there's a couple other ones in between the first problem that we did and this one. So if you look back at the notes, we did really similar problems. So this is actually, I think, the fourth one on the homework assignment. I didn't go over the second and third, but we did really similar ones in class. That's the reason why. So in this one, we have a small 300-gram cart moving at 1.2, frictionless air track, collides with a larger 2-kilogram cart at rest. After the collision, the small cart recoils at 0.89. what is the speed of the large cart after the collision? So really, this is what we did in lab last weekend. If you're there this week, you'll do it this week as well. I need a picture for this one. Maybe that could be mass 1. Oops, yes. Good. Mass 1, mass 2. Mass 2 initially is just at rest. Mass 1, though, has some initial velocity to the right, 1.2 meters per second. So with these problems, it's good to have a before and after picture. This is what's going on initially. We know these masses, too. Just be careful. Mass 1 is 300 grams, so change it into kilograms. That means divide by 1,000. And mass 2 is given as 2 kilograms. So this is initially what's going on. That's before the collision. Now after the collision, mass 1 heads back the other way. And its speed is 0.89. So I'm going to put V1 final, 0.89. Now it's heading back the other direction. So you have to know that that's negative, right? Momentum is a vector quantity. If I'm saying to the right is positive, then back to the left has to be negative. And then we've got mass 2 over here. So mass 2 is going to go this way. And that's what we're trying to figure out. V2 final. So this is really just what you did in lab. And if you haven't done it, you'll do it tomorrow. Okay? I shouldn't say just, because we don't know if this is a perfectly elastic collision or not. It's probably not, but the one that in lab actually is. They interact via magnets. So the initial momentum is equal to the final momentum. Now the initial momentum is just made up of momentum from the first one, because this one's not moving. So this would be mass 1, velocity 1, initial. Now the book likes to write mass 2, velocity 2, initial. But if velocity 2 initial is 0, the momentum is going to be 0 for that one. So I don't usually write that, right? Because it doesn't have any momentum. This one doesn't have any. Now the final momentum, they're both moving afterwards. Mass 1, velocity 1 final, plus mass 2, velocity 2 final. So the big idea with this problem is this is equal to that. So this has got to be equal to that. Okay, so whenever you have a collision, the way to solve collision problems is to use conservation of momentum. That means this. The initial is equal to the final. Okay? And then it becomes an algebra problem. We know everything except for what we're looking for. The only thing that we don't have is V2 final. So let me do just a little bit of algebra here. Mass 1, velocity 1 initial, minus mass 1, velocity 1 final, is mass 2, velocity, whoops, there's a Y somehow got mixed in there. 2 final is what it should have said. Okay. All right, good. I was grading tests and labs all day, so the Y direction's in my head. Okay, that's what I meant though. And then divide both sides by mass 2. And then you can plug the numbers in and solve for this. Just be careful. Remember, this term is negative. Okay? So without putting in numbers in, that's the actual way to do it. Okay, good. All right, any questions on that one? All right. All right, here's another one we can look at, 33. A 2.5 kilogram block slides on a frictionless surface at 1.1. A second block sliding at a faster 4.3 collides with the first one from behind and sticks to it. So So this is called completely inelastic. That just means sticks together. The final velocity of the combined blocks is 2.3. What was the mass of the second block? Okay, so again, it's a collision. Immediately you know the concept to use. The initial momentum is equal to the final momentum. So a picture will be helpful for this one. Okay, so I think it helps to draw a picture too. We've got a 2.5 sliding on a frictionless surface at 1.1, and then a second faster one comes up behind it. So I'm going to call this one M1, and then here's M2. So M2 is going faster than M1, so then after the collision, they're stuck together. And I can write these things down. Okay, mass 1 is 2.5 kilograms. I don't know how much mass 2 is. That's what I'm trying to figure out. So velocity 1, initial means before the collision. Final means after the collision. So this one's moving along at 1.1. And then velocity 2 initial, the faster one, is moving at 4.3. Then they stick together, and the combined group, I'm just going to call this one big V, for the combined velocity is 2.3. And what I'm trying to figure out is what is M2. So when you look through the chapter, there's not going to be an M2 formula anywhere. What you'll find is, if it's a collision, use initial momentum is equal to final momentum. And then hopefully what you're looking for comes out once you put everything together. Okay, so these are both moving this way. This one's moving this way. They stick together. Because they're stuck together, they have a common speed. So initial momentum equal to final momentum. So this would be mass 1, velocity 1 initial, plus mass 2, velocity 2 initial, is equal to their combined mass, m1 plus m2, because they're stuck together now, times v. It might take you a few steps of algebra, but really the only thing that you don't know in this whole long line here is mass 2. So let me distribute the big V through here. Maybe just do one more step of algebra. So this would be mass 1 times big V plus mass 2 times big V. So what you have to do is put everything with M2 on one side of the equation, and then isolate M2 by itself, and then solve for M2. I'm trying to judge your algebra skills. So put everything with M2, which is this term and this term. Say put it on the left-hand side of the equation, move everything else to the right side of the equation, factor out the M2 and solve for it. Okay? I'll just put dot, dot, dot. M2 is equal to something. Okay? Take a couple of steps, but not too bad. All right, great. Any questions on that one? All right, 27. All right, so we have a 300-gram bird. Again, grams perfectly fine, but you'll have to put it into kilograms. Okay, it's flying along at 6.5, sees a 10-gram insect flying straight towards it with a speed of 27, as measured by an observer on the ground, not the bird. The bird opens its mouth and enjoys a nice lunch. So what is the bird's speed immediately after swallowing the insect? So if you picture this happening, it might not even seem like the bird actually slows down, right? Because it's a lot bigger. But the insect is moving a lot faster. The bird probably still does have more momentum. I doubt if a bird would eat an insect and fly back this way, it would have to eat the insect. But it's going to slow down a little bit because before the collision, the bird's momentum was this way. The insect's momentum was this way, but not quite as big. So the net momentum is still going to be that way, but it's going to be less than the bird's value because you're going to take the bird, subtract the insect. So that's before the collision, and then after the collision, the same total amount of momentum. So it's kind of like what we've been doing with these stick-together collisions. It's just now we have a bird and an insect. So we'll have to do a nice picture. Okay, so you don't want to see me draw a bird, so I'm going to draw the bird as a block and the insect as a smaller block. And maybe I'll just call this one mass 1 and mass 2. So mass 1 in my picture here is the bird. So 0.3 kilograms, divide it again by 1,000. The insect, 10 grams, 0.01 kilograms when you divide by 1,000. Make sure I did that right. Here's 10. 1, 2, 3. Good, so 0.01. All right. The bird is flying initially at 6.5 meters per second. The insect is, and it's this way, the insect is moving this way, 27. Now what's wrong with me just writing 27 there? Should be negative, exactly, perfect. Because if I'm saying that this is the positive direction, this has to be the negative direction. Now that's before the collision. Afterwards, here's the insect inside the bird. So there's a common mass here, mass 1, mass 2, and a common final speed. It's one of these stick-together collisions again. Again, whenever you have a collision, initial momentum equal to final momentum. And then we can put in all the details, and hopefully we'll find out what we're looking for. What's the bird's speed after? We're trying to figure out this. Okay? So now initial means before this collision. So we've got the bird, initial velocity of the bird, the insect times the initial velocity of the insect. Just be careful of the sign of this. And then they're stuck together so they have a common mass and a common speed. And then I'll just put ... solve for this common speed. Okay? So you can start to get the theme, right? Whenever there's a collision, whether they stick together, whether they bounce off, the initial momentum is equal to the final momentum. Any questions on this one? It's kind of fun putting in the details. You know that when you do these collision problems, this is always going to be correct. So as soon as you write that, feel good about it, right? Because it's right. And then you have to put in the details and work from there. Okay. All right, good. So there's just a little bit more to finish in this chapter. And it's a couple of problems on two-dimensional collisions. All right, 1 second. So everything we've done has been in one dimension either. Well, it's all been in the x direction actually, but you could have a two-dimensional collision, like if you have you're looking at a billiard table or something like that, and things go in different directions. So this slide just means the same thing that we've done before. These just take longer because there's two directions instead of one direction. So you've got to break this down into x direction and y direction information. So this first line here, this is just the initial momentum equaling the final momentum. This is for the x direction. This equation here is the same thing, but if you notice, it's for the y direction. Now this is like a very general case. 1 plus 2 plus 3 plus however many particles you have. Usually it's going to be 2, maybe 3 different components, probably 2. If it's a collision, you have to have at least 2, right? But maybe one of them is not moving to begin with, so its initial momentum is 0, that sort of thing. So this is just written very general. It could be a whole bunch of particles colliding, like you see here in this this braking situation. There's a whole bunch of different billiard balls going in different directions. The point is, though, that the initial momentum of the system is equal to the final momentum of the system. Okay, just have to be a little more careful because we almost have to do the problem twice. And here's an example of this. 2 pucks of equal mass collide in an air hockey table. Neglect friction. Prior to the collision, puck 1 travels in the positive x direction at 1. Puck 2 travels in the negative y direction at 2. This is prior to the collision. So this is the initial stuff that's going on. After the collision, puck 2 travels 30 degrees above the positive x direction. At point 8, what is the velocity, both the direction and the speed, of puck 1 after the collision? And then this one is similar to 38 on the homework. Okay, so let's work on this one. Again, it's just going to take more time because there's 2 directions involved. Yeah, just like the other ones, we need a picture. Okay, so these are the same amount of mass. Mass 1 is equal to mass 2, 100 grams, or divided by 1,000, 0.1 kilograms. So we got mass 1 traveling this way at 1 meter per second. So velocity 1 in the x direction. And puck 2 is traveling in the negative y direction at 2. Okay. So puck 2 is only traveling in the y direction, and it's actually moving this way, so that would be negative 2. And I'm saying right is positive direction, up is the positive direction, so then down is negative. Okay, so this is initially what's going on. So then they collide. After the collision, puck 2 travels 30 degrees above the x direction. Okay, so this is initially what's going on. And then afterwards, I'll just do afterwards down here. Puck 2 is going this way. This is 30 degrees. And its speed is 0.8. So 0.8 meters per second. And then what is the velocity and direction of puck 1 after the collision? Okay? Let's see if we can get some idea which way puck 1 is going to actually be traveling. So we've got this initially going on. Now if you think about it in terms of momentum, we have momentum to the right and we have momentum down. So after the collision, that's what we have to have. The same amount of momentum to the right and the same amount of momentum down. Mass 2 here has some momentum that's actually got an upward component. So I know if this actually were to happen, if we started with only momentum down, afterwards we only have momentum down. So if this one has a little bit up, mass 1 has to have a whole bunch down, because mass 1's momentum down plus mass 2's momentum up has to equal mass 2 momentum down before the collision. Another thing to realize is all the momentum was to the right, so after the collision, in the x direction, it all has to be to the right. This one already has some to the right. We don't know whether mass 1 is going to be moving to the right, or maybe it bounced back to the left. It looks to me like it's actually going to, mass 1 is going to continue this way and this way. The reason I say that is mass 2 has some momentum to the right, but it's not as big as this one's momentum to the right. So mass 1 is going to have some momentum to the right, and then it's going to have some down momentum. Okay? After the collision. So we have the same stuff before the collision. Just to get an idea what's going on. So some momentum this way, some momentum that way. We don't know how much yet. That's what we have to figure out. Okay? So this is 0.8 meters per second at 30 degrees. Let's figure out V2 final in the x direction, and then V2 final in the y direction. Okay, let me just read it one more time, just to make sure before we get into a lot of work. After the collision, mass 2 travels 30 degrees above. Okay, so this is the correct way that it's going. Okay, so I think that this is something like 0.4 meters per second. So we have an angle, we have the hypotenuse. This part, we could use the sine of theta to get that. I know the sine of 30 is a half, so that's how I have 0.4. To get V2 final, I could say the cosine of 30 is V2 final x divided by 0.8, and then I can get V2 final in the x. So whatever that turns out to be. Something like about 0.7 something, but we'll see in a minute. What'd you get?
169.
All right, perfect. All right, good. So this one is 0.69. This one is 0.4. So we're at the point now where we could actually try to solve this by using conservation of momentum in the x direction and then also in the y direction. What I'm really trying to do is figure out V1 final in the x, V1 final in the y. Okay? So if you want to just think about this as the x direction, this one doesn't even have any x momentum to begin with. This one is the only one that has x momentum. So this is the initial momentum in the x. It's got to be equal to the final momentum in the x. Well, this one and this one both have x momentum. So that's why it takes longer, because you've got to do two different directions. Here we actually had to break things into components. I'm going to get a fresh piece of paper. So the initial momentum x is equal to the final momentum in the x. So this was m1 v1 x. Maybe I should put a little I in there for initial just to emphasize it. That's this one here. V1 initial x. Okay. This is V2 initial in the y direction, just to be clear. Okay. And then the final momentum in the x would be made up of m1 v1 final x plus m2 v2 final x. And then you could do the same thing in the y direction. The initial y direction. Yep. Initial momentum y is equal to final momentum in y. So really we're doing two problems compared to what we were doing just a few minutes ago, right? Because we've got two different directions. So this one is just made up of m2 v2 initial y. Right? Because mass 1's not moving in the y direction. Up here, mass 2 wasn't moving in the x direction. So here then we have mass 1 v1 final y plus mass 2 v2 final y. Okay. So the two things that we're looking for, we now can find. So in this one, the only thing that we don't know is mass 1 v1 final. That's the only thing that you don't know. And same thing with this one. That's the only thing that you don't know. So then it becomes an algebra problem again. So you know what mass 1 is, you know what v1 initial x is, you know v2 final x. We had to do a little bit of work to get that, but we were able to do it, right? That's what this number is. So then we'll be able to figure out that. Same idea in the y direction. The only thing that you don't know is this. Everything else is given to us. So it's going to be a little bit time consuming, but it won't be too bad. We'll be able to figure out V1 final x and V1 final y. Should we take a minute and do it? It's kind of like we've watched this much of the movie, right? Maybe we should see how it comes out. All right, let's do that. So M1 V1 initial x minus M2 V2 final x. So I'm subtracting this from both sides, dividing by M1. That's V1 final x. Same kind of idea down here. M2 V2 initial y. Subtract this from both sides. V2 final y. There's a lot to keep track of, so if you're wondering why does he keep, what's up with all these three subscripts, it's because we've got all different velocities in different directions, initial and final. It's a little bit cumbersome, but it's hard to do it otherwise. And then, so I've subtracted that from both sides, divide by M1, and that will give me V1 final y. Okay? Let me see if I could sneak the numbers in here. Let's do the y direction first. These are 0.1 kilograms. So I'd have 0.1 kilogram. V2 initial y was minus 2. Minus 2, yes. And then minus mass 2. They have the same amount of mass. V2 final y. So that is actually 0.4. Okay? And then divided by mass 1. So that'll give me V1 final y. I think that's maybe minus 6. It's nice that the masses are the same because then it all cancels out, right? Oh, did I write 0.4? I meant 4, I think. Oh, no, I did. You're right. Thanks, Rick. Yeah, it should be a minus, it should be 0.4. So minus 2.4. Okay, that's good. I think that's good. Minus 2, and then this is 0.4. Couldn't read my own writing for a second, apparently. Okay, so minus 2, minus, and then it's a 0.4. So my guess was right that this was going to be negative. Let me slide this back in here. This one. This comes out to be negative 2.4. Okay. Now let's put the numbers in for the x direction. Okay, I'm running out of room a little bit, but I'll try to squeeze them in here. So before we do that, the masses are all the same, so I don't have to write it. Mass 1 and mass 2 are equal, divided by mass 1. They cancel out because they're in every term. So really I just have V1 initial in the x, which is 1 minus V2 final in the x, which was 0.69. Which turns out to be 0.31. So if you notice again, all the masses cancel out because there's the same, they're equal to each other. So all I'm left with really is V1 initial x minus V2 final x. So 1 minus 0.69, so 0.31. Okay, and then I can put that on here if I want to. So here's the recap of the story. Mass 1 was heading this way. Mass 2 was heading this way. They collided. Mass 2 headed off this way. So in response, mass 1 had to head off really this way, right? Because it's got a x part and a y part. So you can kind of picture that happening, I think. And we had to conserve momentum in the x direction independent from the y direction to come up with these values. This is the y part. All right, so again, this was the hardest problem of the semester, right? Every once in a while we get one of those. But really, it took a long time to do it. There's all these subscripts, but really, you you have to keep track of what you're doing, and that's the way to do it with the subscripts. Okay? What's that? So that's the x part and y part. If you want the overall velocity, is that what you're saying? Yeah. So we can get the overall velocity. We've got the x part and y part. So the overall, the total velocity of this mass 1 would be the x part squared plus the y part squared. That's to get the overall amount. And you could actually get this angle if you wanted to as well. So the tangent of theta would be the x part divided by the adjacent part, which in this case is the y part. So then theta, inverse tangent of x part divided by y part. And that's defining that. Okay, yeah, very good. So it's even harder than I originally thought if we throw in that part. That's good though. All right, excellent. Now the one in the homework is actually, they stick together after the collision. It turns out if they stick together, it becomes a little bit easier, mathematically speaking, because with this one, they didn't stick together, so you have to look at this one, and then you have to look at this one alone. And the homework, they stick together and move off with the common speed, so the homework one's actually a little bit easier than this. You'll see when you do it, mathematically, it's a little bit easier. Okay, good. Any other questions on this one? All right, so let's look at one more, and then we'll jump into chapter 10 a little bit. So I opened this with Chrome. I've been using Firefox, but I wanted to see what Chrome looks like, and it kind of didn't open very nicely. It's all kind of goofed up there. So I'll stick with Firefox in the future, I think. Anyway, with this one, if that happens to you sometimes, change browsers. Usually it was like Explorer, or whatever they call Explorer now, Edge or something like that. That one used to have a lot of problems, but it seems like it works a little better than Chrome recently to me. But maybe this just needs to be updated or something, this version. Anyway, a firecracker and a coconut blows the coconut into 3 pieces. So it's kind of the opposite of a collision, but it's still an internal force. So we could use conservation of momentum for this one. A firecracker, blows a coconut into 3 pieces. 2 pieces fly off. 2 pieces of equal mass fly off south and west, perpendicular to each other at 25. The third piece has twice the mass. What is the speed of the third piece? And then what is the direction of the third piece? Okay, so we've been doing collisions. It could also be an explosion. The reason being, it's an internal force. Okay, so let's set this one up. Okay, so let's see. 2 pieces fly off. One is south. And one is west. So this is these are kind of problems that are a little scary. Like, they just say they just say it's a mass. They don't say how much. That's okay though. We'll just work with it and see if the mass actually cancels out. This is an M, believe it or not. This one's speed is 25, and then this one's speed is 25, and then the direction just tells you which way it's going. This one's down, this one is to the left. So before this explosion, there was no momentum. So after this explosion, there's not going to be any net momentum. This is the kind of one that we did with, I think it was David and Sarah. David had more mass, Sarah had less mass. David pushed Sarah, they were on ice. Sarah went this way, David went that way. the way we solved that was there was no momentum to begin with. That was an internal force between David and Sarah. Although Sarah and David had individual momenta, if you added them together, they added up to 0. So there was no momentum before this collision of David pushing Sarah. So afterwards, there's no net momentum. David's momentum this way was balanced by Sarah's momentum that way. This is really the same thing. This thing is exploding into 3 pieces, and we want to know how fast this third piece is moving. Well, before this explosion, there was no momentum in the x direction. So afterwards, there could be no momentum in the x direction. So I'm saying that this big mass has to be moving this way at 12.5, and it's got to be moving this way at 12.5. The reason is, in terms of momentum, this has 25 times m. This is 2m times 12.5. Those balance out. We've got the same momentum this way as this way. This is m moving at 25. Oops. This is m moving at 25. This is 2m moving at 12.5. It's the same amount. Same thing up and down. They tell us this is m moving at 25. This has to be 2m moving at 12.5. So really we're using conservation of momentum. Whatever's this way is balanced by whatever's that way. Whatever is down, which they tell us, has to be equal to whatever's up. And then it works out that this has to be 12.5 and this has to be 12.5. So this is the x part, this is the y part. Like the previous problem, we'll have to get the overall. So the overall would be 12.5 squared, that's the x part, plus the y part. You can't just add them together and say 25. You got to add them like this. So 1.4 times 12.5, whatever that turns out to be. 12.5 plus 0.4, 8. Yeah, so whatever this turns out to be. Close to 13, I would say. Maybe a little bit more. Yeah, definitely more. 16 maybe.
$17.6.
17.6, very good. And then this angle's got to be 45 degrees, right? If this side's 12.5 and this side's 12.5, that only happens if this is 45 degrees. So that's, the first part is about 17.6. You can't see it. The second part says, what's the direction? And we came up with 45 degrees. So this is the overall velocity, and then at 45 degrees. Okay? Very good. All right. I guess I'll just say one more thing about this. You might say, well, how did you just know it was 12.5? If I was actually going to set up the x direction, I could say m times 25, and everything's in SI units. This would be equal to 2m times velocity in the x. Right? This is just looking at the x momentum. And I left out the units here, but it's meters per second. And then the m's actually cancel out. And then you get 25 over 2. Turns out to be 12.5. Okay. All right, good. Any questions or comments on that one? So you've got a week to do homework 5, but we won't actually be meeting until next Wednesday. We can talk about it. It's not due till Wednesday at midnight, so we can talk about it in class Wednesday. But try to wrap most of it up before you come back to class Wednesday. Okay? Good. So there's a little bit about the chapter on angular momentum. We'll come back to that when we do circular motion. So if you read through the chapter, angular momentum, we'll be coming back to that. Good. Do you have the energy to go on to the next chapter? Good. It's very appropriate because the next chapter is on energy.